Okay, hello everyone. Let us start our session in about a minute. Okay, then let us start. So I hope everyone is watching the tutorial videos which has been done in past few weeks. Today is week 11. Also, everyone is completing their assignments, watching the lecture videos taught by the professor. Today we'll be starting with the simple algorithm, and we'll see few questions related to that as well. All right. So let me just share my screen. I guess let let us just wait for about a minute more so that others as well join session, because today's session is going to be very interesting for sure. Meanwhile, let me share the screen. Okay, I hope my screen is visible now. Okay, I guess people will join me, right? Let us start now for our session today. I hope my screen is visible. Maybe my camera is not functional. Okay, anyways, I guess it will take time for my camera to get functional. I'm trying my best. If my screen is not visible, please let me know. Okay. All right. So I guess whatever I'm writing is visible on the screen. Now, I guess it's showing some error related to the presentation of screen. Your screen once again. I guess screen is now clearly visible. Yeah. Okay. Yes. Okay. So we have dealt with a lot of different boundary conditions, either for convection problems or diffusion problems. So like Neumann, Dirichlet, or mixed type of boundary conditions. Okay. For diffusion kind of problems, but for convection kind of problems where the flow boundaries are happening, like inflow boundary condition requires, outflow boundary condition require, where flow enters or leave the computational domain, or there are kind of geometric wall boundary conditions. So inflow, in case of boundary conditions, let us say, so like inflow kind of boundary condition, inflow boundary condition, where you say that the convection term, which is uh, del dot, sorry, convection term, del dot rho u phi. Okay, rho u phi is there. So where you have a density of a particle, you have the velocity of the particle or any property phi you want to calculate. So suppose you have a kind of a cell like this. This is a kind of a cell at the boundary. Okay, this is your C naught. Okay, and the area vector for this is AF of this space. Okay, this is your boundary. So this is an inflow kind of boundary condition when suppose your velocity is going like this, okay, in this direction. So let us say, sorry, u at boundary. Okay, so area of boundary. Let me write area of boundary. Okay. So if you see the dot product of UV dot AB, is it greater than or less than zero? Is it less than equal to zero? Because these two are pointing in opposite directions. So when the dot product is less than zero, then we say that it is a kind of inflow kind of boundary condition. Inflow kind of boundary. All right. So there are discrete equation for the boundary cells. So you know the summation of for the diffusion terms for interior particles, exterior particles, that is boundary particles. Okay. So there are terms corresponding to that. But if you want to treat the boundary phases, you have to give the conditions like this. Okay. Similarly, if you go ahead with the outflow boundary condition, outflow. So that means the fluid is flowing outward of the boundary. Okay. Suppose this is your again cell here. This is your cell. This is your cell here. Okay. And this is suppose again this is some C naught. So velocity is pointing out here, UB, as well as your area of that boundary of that cell. Both are pointing in same direction. So UB dot AB will be greater than 0. So you can say that this is kind of an outflow kind of boundary condition. Outflow kind of boundary condition. So I've basically in brief I've discussed what is an inflow and what is an outflow kind of boundary condition. So what are the implications you can say in inflow and outflow kind of boundary conditions? So if you want to uh, write the discretized equation, as I said, okay. So if for inflow boundary condition, the dot product is less than or equal to 0, then we call that is an inflow boundary condition, dot product of UB and AB. So if you want to put these in the equation back, put these in the discretized equation. So you have discrete equation for boundary cell. So in that scenario, suppose your equation was like this. Summation of over all the faces grad phi of all the faces dot AF minus F. Here F are all interior, okay, are all interior. Rho U phi of F dot AF plus. So these are interior cells, okay, inflow and outflow which is happening. Okay, and there are boundary cells as well. So this is your diffusion term, this is your convection term, okay, plus that phi of B dot AB minus rho U phi B dot AB, okay, plus some source terms are there. Source terms SC delta V, okay, delta V naught is equal to 0. So the terms which are corresponding to the, so this is a discrete equation for boundary cell, all right, this is a discrete equation for, this is it. There are discrete equation for boundary cell where we basically have the diffusion terms, okay, we have the integral terms, which is for the first term as I told, and we have the convection term that is rho U phi. So for interior faces, the triangular cells are here that are basically two interior faces, and then we have not written the boundary face, which is we have written the boundary face, which is the this represents the boundary part, this one, and this represents the interior face, okay, interior, and this represents boundary. All right. So okay, and the source terms. So this is our original regular equation, but written in terms of separate out between interior as well as boundary cells. Okay. So we know how to kind of discretize these interior faces already. We have done this kind of thing in our previous tutorials. We just need to look how to discretize the boundary terms. And only thing that needs to understood is that how do we discretize the two terms? That means if we look at the two terms, even if you can say the first part which corresponding to the diffusion one is already known to us, we know how to discretize this. So this is basically it gives the rise to coefficient dou phi by dou zeta if you take the boundary cell zeta direction, and other coefficient terms of eta. You take zeta and eta directions. Already done this kind of thing. Okay. So I was saying zeta and eta kind of thing. So if you say the convective part in which the rho bar is known, rho is known basically. The density at the boundary is known, velocity is known, phi is known, AB is known. Okay. So we know essentially everything is known to us at the boundary face, because that's a kind of a boundary condition which is given to. Then again, coming to the outflow boundary condition as well, whether it's earlier it was for the inflow boundary condition. For the outflow boundary condition, we said that dot product should be greater than 0. So again, if we say for the outflow boundary, that means we call the particular cell again a cell that has shades of faces in the outflow. Okay, all right. So you are saying that the dot product is positive in this scenario. So the outflow boundary is a kind of boundary where things happening inside needs to be kind of dictate what I'm actually leaving through the outflow, depending over the flow rates. Okay? So essentially, we do not know yet what needs to be specified essentially. So we cannot specify anything as of now. Because if we can say, if we feel that whatever is being computed inside that, so at the boundary, all the values are being known. But when you are specifying that what is a kind of boundary condition, so it's an inflow boundary condition or outflow boundary condition. Okay. I hope it is clear. Any other doubts? Next is a scenario where geometric boundary condition is happening. So in detail, everything has been discussed in the lecture videos. Geometric boundary is a kind of boundary like this. If you say you have flow, this is your area vector of that face. Okay, you have a impermeable wall. Okay, at the walls. If you see that your flow is like this, okay, at this boundary. So here UB dot AB both are perpendicular to each other. That means the dot product will be 0. Dot product will be 0. So if you go in the equation, that means UB dot AB. Suppose you write your equation back. So gamma grad phi of P dot AB minus rho U phi of B dot AB. So if you observe here, this U dot AB will be 0. Okay, at geometric boundary. At geometric boundary. So 3 different kind of boundaries we have dealt with: Raman, Dirichlet, and mixed kind of boundary condition for diffusion part. And in convection part, we have done with inflow outflow boundary condition and geometric boundary conditions. So coming to the solution of, you say, fluid flow equations. So let me write that. Solution of fluid flow equation. Okay. So if you have a general transport scalar equation like this, dou by dou t rho u plus del dot rho u. In terms of fluid, I'm saying now. So momentum equation I'm writing plus some source terms. Okay, minus dou p by dou x. If I want to write in x direction, if I'm saying instead of property u for a general, you will say the term here will be phi. Term here will be phi. Okay, but I'm writing in terms of u. Okay, so the every component, every kind of discretization, we have seen how to solve the diffusion part, convection part, and steady part. So in principle, we can now solve for the convection diffusion equation or a general scalar transport equation for the scalar phi or u. So if you look at the fluid flow equation, we basically have a similar kind of structure. The only thing is that instead of phi, there comes a u and v. So instead of one equation, we will have having two equations. So if we consider a 2D kind of scenario, okay, the x and y direction, both side the flow is happening. Okay. Instead of one equation, we'll be having two momentum equations, x momentum and y momentum equation, where phi is replaced with u and v. Also, we have a continuity equation in addition to these two equations in fluid flow problems. Okay. So if we compare, our equation will be like this compared to the general transport equation. All right. So let me write the discretization of steady momentum equations. So we assume that flow is steady, incompressible, and Newtonian. Okay, steady, incompressible, and Newtonian. Okay. This is a four. How we discretize this momentum equation? We have to make some approximation. These are the approximation. Steady, incompressible, and it is a Newtonian fluid whose shear stresses are proportional to the shear rates. And we go ahead with the solution of the fluid flow equation. We can start with like a uniform or a structured mesh, which is basically a Cartesian mesh. So let me draw that. Okay. So suppose my cell of consideration is this. This is your P. This is your east face. This is your west face. This is your north face. This is your south. This is your delta Y. And this is your delta X. All right. Right. And U and P are being stored at center. Here, U and pressure, velocity and pressure are being stored here. Okay. So your equation for the X and Y momentum equation will look something like this. Del dot rho u is equal to del dot mu del u plus S of u minus I dot del P. Okay. In the I direction, similarly for the Y direction, the rho u v del dot mu del v plus SV minus J dot del P. Okay. The pressure term. SU is a body force. SV, suppose, is some miscellaneous velocity gradient. So these are our X as well as Y momentum equation. Okay. So we say that SU and SV do not just contain the body force terms, they also contain all the miscellaneous velocity gradient terms, which we don't write in the viscous terms. And depending on the value of the viscosity, we take all other terms and they will actually be go to zero, as well as there's a possibility for that. Then if we want to apply a finite volume to the two equation, we know how we can solve for both of them. So if you want to apply the finite volume, FVM, it will be del P dV. So your pressure terms over the control volume will be over the control surface by GDT P dot equal to summation of all the forces over the faces PF, AF. Okay, this is clear. We are focusing on the grad P term if you are going to apply the finite volume method. So by GDT, it will come like this, and summation of all over the faces. And the cell centroid value or the phase centroid value can be used to represent the pressure on that phase. Then if this PE, if you want to write for that particular phase, so that can be east, west, north, south, corresponding to that. So in the x momentum equation, how you will corresponding to the x momentum, how you will write it? It is minus I dot del P dV over the control volume. This was our expression here of the momentum equation. This, okay, all right. So I've not written this negative sign. Okay, minus I dot del P. And we applied a FVM technique. So this is our minus I dot summation of all the faces, PF, AF, where faces are east, west, north, south. So it can be written like negative of PE, AE dot I minus PW, AW dot I. You're doing the dot products for all the faces. So it will be how much? So if you say AE dot I, both are in which direction? Both are in positive direction. So at this east face, this is your east face, this is your west face, this is your north face, this is your south face. So area vector as well as east, both are pointing in same direction. That will make it positive. And already there is a negative sign outside. So that will remain negative PE del Y. Whereas if you go for west is in pointing, area is pointing negative x direction, dot with I, it will be negative. So negative outside and inside negative gives you positive. PW del Y. Okay, PW del. Then if you go with the Y momentum, whereas for north and south, even if you do, the dot product will be 0 because I hat is this direction and area vector is pointing in this direction, area of north. So both will be 0. Okay. Similarly for Y momentum, so the influence of area vectors of north and south will come, east and west will drop out. So your equation was J dot del P dV over the control volume is equal to minus J hat summation of for all the faces PFAF. So again, the contribution will come from north, En dot J minus PS AS dot J. So again, north and area both are pointing in same direction. So we can directly write PS into Pn dot del of X. Like here I was writing PW minus P into del of. So this is a pressure contribution, discretization. You have written. Now our equation was have other terms as well, which we have already done. On the pressure discretization, we have not done, but viscous, that is just the diffusion part, and the convection part we have already done our previous tutorial. So how we can write after putting it back, our equation will something look like this: APUP, because velocity instead of phi, our variable is u. We want to calculate u. Here the neighboring nodes ANB, UNB plus BN plus the first term PW minus P east. This one PW minus P is delta Y from X, and from Y momentum it will be NB NB VNB plus BV plus PS minus P north del X. Okay. So now there's a linear profile assumption for pressure, and assuming it is a uniform grid. So assume linear file assumption. We are dealing with a uniform grid. So how you can write P east can be written as, so your cell was this, P east can be written as PP plus PE by 2. PP plus PE by 2. Similarly, P west can be written as PW plus PP by 2. P north can be written as P north plus PP by 2. And P south can be written as P south plus PP by 2. All right. Is it clear? Are there any doubts? Just we are doing a linear profile assumption. So here in our above equation, both pressures as well as velocities are unknown. Don't know. So far we were assuming the last lecture that they are known, but right now we don't know. Okay. And we assumed a linear profile assumption because so far we are saying that our values of the velocity and pressure are being stored at cell centers. These are not stored at phase values. Okay. So P east, P west phase values are not known. So you apply the linear profile assumptions for this, correct? So if you substitute all the values back in the equation, so if you observe in the equation, PP comes on both the sides, comes up in both the, sorry, both the sides, not both the sides, both the equation, and there is a minus. So we come across with PW minus E. Okay. You try to put it, put these values and tell me. So either it's a X momentum or Y momentum equation. The PP comes in X momentum as well as in Y momentum. Okay. That is what I'm trying to say. In both the equations it comes. And if you put all these values in the equation, see your first term PW minus PE, what it will be if you put back. So PW minus PE is, PW is how much? This is PW plus PP by 2 minus PP minus PE by 2. So this cancels. So you are left with PW minus PE by 2. All right. Into delta Y if you will do. So I will just, and you after putting these values. So what we have done basically, we have converted the phase values into the cell-centered values where pressure was getting stored. The pressure was getting stored. So if we know P, then we can find use the equation 1 and 2 and calculate the U. If we know the cell-centered values of east and west, then we can get the value of U by putting the pressure in that equations. Okay. But pressure itself is unknown. So the other equation at our disposal is the continuity equation. All right. Now, using which we hope to obtain a pressure field. So both are known. So in this equation, this pressure is also unknown as well as velocity is also unknown. Correct? Both are unknown. So how you will get the values? So let us do the discretization of continuity equation. Correct? Dou by dou t of rho plus del dot rho u. It's a steady equation. We have assumed that this will be 0. Then just apply the FVM over PV control volume. After applying the GDT, it will be rho u dA. So that is nothing but summation over all the phases of rho u dot AF. Okay, over all east, west, north, south phases. So you can write like this: rho u east delta y minus rho u west delta y plus rho u or v because it is in the y direction. North delta x minus rho v south delta x equal to 0. However, UE, U west, VN and V south are not available to us because U is stored only at east, west, north, south, right? And these are the phase values. These are the phase values, not cell-centered values. Okay. So again, you assume a uniform grid and linear profile assumption. Assume uniform grid and linear profile assumptions. So what you will get, rho u of east you can write as rho u at E plus rho u at east by 2. Similarly for west phase and so on. All the values you can get. Okay. And you can put back. So what you will get? The equation will be like rho u capital E del y minus rho u capital west del y plus rho v capital north del x minus rho v capital south del x equal to 0. No UP VP feature in the above equation if you observe. Only the neighboring nodes values, the cell-centered values are known here. So the cell which is wanted to be under consideration is not. Okay. If you observe here, no UP, capital P, and VP feature in above equation. All right. I hope no doubts still here. Okay. And because we are writing the equation for cell P, and none of the values of cell P, that is U or V, corresponding to that cell P is featuring in this equation. But the values of the particular cell are not in this equation. That is something very having some strong implications. So we will see what will be the implication does it have because of this thing. So essentially, because of UPVP not featuring in the above equation, we'll see there is a major consequences of that or you can say major trouble, which will affect our solution process of the solution or procedure. So equation, that means this kind of equation, because your UP, VP do not feature in this equation, this can actually support a checkerboard kind of velocity pattern. Okay. For example, if U east and UW are of the same value, however, they are different from the value of UP. Or if you say U east equal to UW, however, they are not equal to UP. Similarly, V north and V south, but they are not equal to VP. Then this equation can still be satisfied, although there are oscillation in the velocity field in this equation, which will still give you a conserved continuity equation. So suppose what I'm trying to say is that your problem has become like this. Okay, this is a uniform grid. Suppose this was your cell under consideration with U is equal to 30. This was a cell of consideration. You write with red color. U equal to 30. This is a cell P. Okay. I will highlight it. Now, previous cell has a value of U equal to 10, as well as east well has also U equal to 10. All right. Here V is equal to 20, and here also V is equal to north and south both have 20. Okay. If this is U has 10, then again here you will be 30. Here you will be 30. Okay. Suppose here V can be 40. V can be 40. Okay. This kind of problem can be created. And here V can be 40 again. V can be 40. So in cell P has a 30, but its neighbors are of same values, either in east-west or north-south. So this is a kind of a checkerboard kind of problem, which is satisfying the equations, but it itself is not taking the value and satisfying the continuity equation. But what about the momentum equation? If the momentum equation sustain this pattern, then final Ux and Vx will contain checkerboarding. As well as P is also unknown with us, if you remember. Both P and Q are unknown. If you recall our equation, this is something like checkered board. Checkerboard kind of scenario. All right, checkerboard. So if you recall your equation, that was APUP, X momentum, summation of A and B, U and B, okay, plus B, U, plus P at W, capital W, P at capital E, into del Y. So it is possible to arrive at a P such that gradient of P cancel out the checkerboard velocity bits as well, thereby satisfying the checkerboard velocity. So if you assume for a cell P again, so again make a grid. This is your grid. Okay. So your cell under consideration is this. Okay. Here P is 5, suppose. Okay. Then here P is 10. All right. Here P is again 10. Here P is 5. Here P is 5. All right. So your cell under consideration was this, suppose. So at the cell, if you observe, here and here, both side pressure is same. But here and here pressure is different. There's a pressure gradient. So what is happening to this part? This part is becoming zero because in our momentum equation, P at P is not there. Only in west and east is there because that cancelled out when we wrote a linear profile assumption uh, for the uniform grid. So this will cancel out. But in actuality, the flow is happening. There is a gradient of pressure crossing through P. But this equation is saying there is no gradient. Pressure gradient is zero. Because we are not interested in the absolute pressure values. We are interested in pressure gradients. So which is an unphysical kind of thing. Okay. This is kind of an oscillatory behavior of pressure field in X momentum equation, where it is saying that gradient of P, if this kind of scenario occurs, it is not always that pressure boarding will happen, checkerboarding will happen. But if this kind of pattern develops, that for considered cell, both left and right faces are of equal values, then what will happen? Checkerboarding will happen. So that means here, gradient of P will become zero, correct? So which create oscillations, unwanted oscillations. Wiggles are there in U and P values of the final solution, which cause the divergence of the solution. Therefore, wiggles of U and P, this implies divergence of solution of your solution. There's a divergence of your solution. Now, how to tackle this thing? This kind of thing is a staggered grid approach problem we have to deal with. We are dealing with the simple algorithm. We will deal with simple. So we have identified two difficulties so far. One is checkerboarding of the pressure and velocity. Second is no equation for pressure is there because that equation of continuity does not involve pressure terms, but pressure and velocity both are unknown. If you have pressure, then only you can get the velocity out of it. Okay. So there are two issues, checkerboarding. So you have issues, checkerboarding of P and velocity. Second, no equations for. Okay. So what we will deal with, just give me a minute. I'll be back. Okay, let's start. So we came across with these issues. So what we can say, staggered grid approach. It is a remedy for checkerboarding. So we realize that checkerboarding is a result of storing U and P both at the same cell centroid locations, or you can say co-located or collocated locations. Co-located location. So instead of that, what will you do? Use a staggered storage grid approach. Because earlier we had a cell P where at this cell centroid value, U and P both were getting stored. That was an issue. Instead of that, what we will do, let me make a new grid. Carefully understand this grid. Okay. So suppose this is your cell. At cell centroid, the pressures are being stored. Whereas your velocities will be stored at half dx by 2 of to the cell centroid. So you can say that your velocities are being stored here. Suppose this is u east, u west, v north, and v south. Right? V north, v south. So that means we have two control volumes for velocities as well as for pressure. So if you observe, the pressure our control volume is this. Okay. Whereas for the velocity, the control volume will be like this. This is a y velocity. So I'll make somewhere outside instead of getting confused here. So your flow is happening like this. All the velocities are being stored here. All the vertical velocities are being stored here. Essentially, we are changing the position of pressure and velocity storage. Okay. There is a control volume for velocities and for pressure. So let me make a very clean diagram of one of the cell center. So this is a cell P. The pressure has been stored. Okay. It's a bit complicated, like clearly like this. Correct. Okay. So this is a control volume for your velocity. Okay. This is your control volume for your P. And this is your control volume for. So this is your control volume of U. This is your control volume of V. And this is your control volume of pressure. Three control volumes are there. Okay. This is your cell. Okay. Whereas density, divided gamma and phi are at central coordinates. Cell center radius. So for your cell P, you have U east, U west, P north, P south, and pressure is being stored. So you need to discretize the continuity equation on cell P. Always make sure that discretize continuity on cell P. That is del dot rho u dv control volume equal to 0. That will be summation over the faces rho u for the phase dot a of equal to. So this is your primary control volume. Cell P is your primary control volume. Based on that, you have U and V control volumes. U and V control volumes. Okay. So your continuity equation will look like rho U east minus, sorry, A east. That is nothing but delta Y. A east is delta Y minus rho U west delta Y plus rho V north delta X minus rho V south delta X equal to 0. Again, U east, west, north are not stored at cell centers. They are stored at velocity control volumes. Okay, that is our fix. So this time we don't need to interpolate these because these are not stored at cell centers. The velocities are readily available at the cell faces. We have a control volume for it. So this eliminates the velocity for checkerboarding. Okay, we have these available values stored at the faces this time. U east, U west, V north, V south, stored, or let me say readily available no need to interpolate. Okay, no need to. Now comes discretization of x momentum and y momentum equations. So we already have that momentum equations. So x momentum, the x momentum equation using the control volume you have I dot summation of phases PFAF. So here phase will be E and P. So that was PP and PE del Y already done above. And Y momentum was from above minus J dot summation PFAF north and P is equal to PP minus P north del X. Okay. So we don't need this eliminates the pressure checkerboarding because we don't need to interpolate. We have already got this. Eliminate checkerboarding. Here also, because we have directly we have added the cell-centered values. No need to interpolate. Eliminates checkerboarding. All right, eliminates checkerboarding. Now, so what staggered grid has done, it has avoided the result. Staggered grid results in avoidance of pressure and velocity checkerboarding. All right. So you have the discrete momentum equations like this. Therefore, AE UE is equal to summation of A and B UNB plus del Y PP minus PE plus BE. And AN BN is equal to summation of ANB PNB plus del X PP minus PW plus BW. Okay. Yeah. I hope it is clear. Any doubts? Neha, Sandeep, do you have any doubts? So we have the discrete momentum equation and the discrete continuity equation, but still we do not have any equation for pressure. So now what about the neighboring values here? A and B, U and B in the context of collocated approach. These U and B where east, west, north, south, and so on. So we have done that all the way through, but now because we have shifted these things for U and B are also now differently. They are not capital E, capital W. For example, if you look at AEUE, essentially we are talking about this. So what will be the neighbors of for this? This has something neighbors which we'll use to call the phase pair, which is between capital E. Okay. Then the neighbors are little e, little w, north, northeast, and south, southeast. Okay. So there are u and v's that we have to use while writing this equation. Because we are saying that they are being stored, but these u and v are being used while writing this equation. Similarly, A and B and B, we have to use while writing the equation for north, that is Vn, is basically north, north, and south, and northeast and northwest. Okay, so if I make the grid back again, okay, this is your grid. Suppose this was your P. This is your north, this is your south, this is your east, this is your west. Okay. Right. So this is your east, this is your west, this is your north, this is your south. Okay. Velocities are going like this. U east, U west, V north, V south. Now this velocity at east has the neighbors. This, this, as well as, you tell me. I'm writing these as northwest, this as southwest, this as southeast, this as northeast. Okay. Again, they have faces. Okay. Is it clear? Like for which face we are dealing with? That face has the corresponding neighbors. East face has P, E, the north, northeast, south, southeast. Okay. Similarly for other faces also. Okay. So the simple algorithm is fix the second difficulty. So first difficulty was first issue, checkerboarding of pressure and velocity. Second is no equation for P. Staggered grid, making a staggered grid eliminates the difficulty for checkerboarding, and using a simple algorithm fix the second difficulty. Let's just wait. Just give me a minute. Okay, let's start with the simple algorithm. Okay, so it is a semi-implicit method for pressure-linked equations, which addresses both the difficulties, use of staggered grid approach, and create a discrete equation of pressure from the discrete continuity equation and the discrete momentum equations. In detail, everything has been discussed. So we had three control volumes, one for U, one for V, one for pressure. U means X momentum, V means Y momentum, and continuity equation for pressure. So what we will start with, we'll start with a gas field for pressure. Start with gas field for pressure. So we will assume that it is P star instead of. So solution of discrete X and Y momentum equation with P star will yield solution of X and Y momentum equation with P star will lead to U star and V star. Okay, that is AE, your X momentum equation, AE U V star is equal to summation of P and B U and B star plus del Y P star minus PE star plus BE. Okay, and AN VN star is equal to summation of A and B, P and B star plus del Y P naught, sorry, PP star minus PN star plus BN. Okay. So you get the solution of this equation as UE star and UN star. Because you have guessed P stars, you will get UE star and UN stars. Right? First thing. Solution of equations. Okay. Now, because these are solution of equation UE star and UN star, because P star is the only guess, and UE star and VN star does not satisfy continuity. These are the guess from the guess value of pressure, you're getting guess value of velocities. Not the guess values, you're getting the velocities out of the guess pressures. Okay. So, but they will not satisfy the continuity equation. Not satisfy continuity equation. Okay. That is, you cannot write like this, rho E star delta Y minus rho U V star delta Y plus rho V north star delta X minus rho V south star delta X is not equal to 0. Okay. So let's propose correction to U star, V star, and P star. Okay. Such that it satisfies both momentum and continuity equation. Correction to U star, V star, and P star to satisfy both momentum and continuity equations. So let us do. So we can write the original velocity u, actual velocity is summation of u star plus u dash. Similarly, v is equal to v star plus v dash. Okay. Correction that u star and v star are the corrections because u star is not equal to u. That is why it is not satisfying. If u star is equal to u, that means it is satisfying the continuity equation because the actual u is satisfying the continuity equation. But the u star which you have got from the p star is not satisfying the continuity equation. That is why you have to add some correction such that you get the velocity, u actual velocity, which is satisfying the continuity equation. Okay. Similarly, p is equal to p star plus. So your actual equation was, suppose this set of equation is 1. Okay, in the star. Your actual equations were these. AE UE is equal to ANB UNB plus del Y BP minus PE plus BE, and A naught V naught is equal to summation of ANB VNB plus del X PP minus V naught plus PV. Let us say this set of equation is 2. Let us subtract both of them. 2 minus 1. We should do 2 minus 1. So UE minus U star is U dash. U minus U star is U dash. Right? I'll write for 1. U dash is U minus U star. Same thing I'm writing here. So it will be AE UE dash equal to summation of A and B UNB dash plus del Y PP dash minus PE dash. Rest B terms will get to 0. N dash dash PP dash minus P naught dash. Okay. This set of equations, let us say, these are the corrected terms are included in this equation. Okay. So as per the simple algorithm, we need to solve this two system of linear equations to get the value of dash values, so that the U star and U dash both combine to get the actual velocity field, which will satisfy the continuity equation. So here's an approximation in the simple algorithm. We assume that in this, the contribution, so basically the contribution is coming from dash velocities and dash pressures, and corrected velocity and corrected pressures. So we assume that in this, assume that the contribution for calculation of the velocity at E and corrected velocity at E at naught, east and naught, the contribution from this will be 0. Okay, this is our assumption. Simple makes an approximation. Okay. This is your approximation. Therefore, you can say that it is AE UE dash is equal to only just E dash minus PE dash, and EN dash is delta X. All right. Right. So this is our approximation. So from the equation 3, the contribution of summation of A and B, V and B has been taken to 0, is dropped. This will have a consequences. The P dash takes the entire balance now. Only the P dash takes the entire balance for calculation of U dash and V dash. But here we no need to solve this for the system. No need to solve for the system now. System of equation. From here directly, you will get sorry, PN. All right. So we'll say that this is TE, and we'll say that this is TN. Okay. Now you can put back these values in your actual equations. Since U east can be written as UE star plus U dash. Put the U dash, UE dash. Yeah, that will be UE star plus PE, PP dash minus PE dash. Similarly, V naught will be Vn star plus P naught, PP dash minus. Okay, now you have got U and V. Now, what about the flow rates? What about the flow rates? Flow rates, for the flow rates, we can write like this, that flow rate rho into U is nothing but summation of Fe star is Fe dash, because flow rate itself has U values, no? So you have done above here. These U values you have calculated. Put these values rho U E star del Y plus rho del Y PE PP dash minus P dash. Similarly, F naught can be written as rho V naught star Lex plus rho del X P naught P dash minus P naught dash. Okay. Now let us say, because not let us say, this is your basically UE dash, and this is your VN dash. These are your values rho into V. So we know that UE star and VN star do not satisfy the continuity equation. Similarly, the flow rates will also not. Okay. Therefore, since Fe star minus Fn star Fw star plus Fn star minus star is not equal to 0. We know that thing. But the collected values do satisfy the continuity equation. But Fe minus Fw plus Fn minus Fs is equal to 0, satisfy continuity. So Fe is nothing but Fe star plus Fe dash. Similarly, F naught star, F V star plus Fw dash plus F naught star plus Fn dash minus F south star plus dash equal to 0. Now you know all the values, so you can say that Fe star after rearranging minus Fw star plus Fn star minus Fs star is Fe dash minus Fw dash plus Fn dash minus Fs dash. Taking star values here and dash values separately. Correct? But Fe dash, you know what is Fe dash? We just calculated. This is your Fe dash. Okay, rho dE del y. Similarly, FW dash, all the values you know. Now substitute back in this here. So what will you get? Substitute in this equation. Try to substitute and tell me. So if you substitute back, so let me write here dash values and here star values. Dash, 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 dash. Here are the star values. After substituting, you will get rho dE del y dP dash minus PE dash minus rho dW and so on plus rho dN del x P dash minus P naught dash minus rho ds into the value is equal to F E star minus F V star plus F N star minus F S star. Okay. So write it in the standard form. Therefore, you can say that it is AP PP dash equal to summation of A and B, PNB dash plus. So this is an equation of ratio. Now you have got from the continuity where AE is just AE is A west not AB. You can as AE is just rho DE del Y. Similarly, A west you will get rho DW del Y. A naught you will get because here capital values are coming because all the values are stored at cell centers. Rho dN del X A south rho ds del X. And AP is nothing but summation of A and B is nothing but your star terms. Okay, this is our equation. So if P star were correct, then it would yield U star and V star that satisfy both the momentum and continuity equation. And if B is equal to 0, then what happens to this P dash in this equation? If P is equal to 0, this is 0. What happened to the continuity equation? Oh, sorry, what happened to the P dash if B is equal to 0? What about the velocity corrections? Everything is solved. You've got all the coefficients, AP, east, west, north, south. Think about that. When B is equal to 0, your equation will become like this is equal to this. Okay. So what will be the Scarborough criteria? Is it satisfied? Because we have to solve for the system here. This is an equation of system of linear equation. We have to solve for pressure correction equations. This is a pressure correction equation. So we need to know whether Scarborough is satisfied in equality or inequality. It is satisfied in the equality, because equality condition is basically satisfying here when B is equal to 0. Because AP is summation of all the coefficients. So this will satisfy this car, bro. So let us make some comments in terms of what will happen, how do we solve this equation. Now we have arrived at this equation for pressure correction, which is basically an equation for pressure itself. Instead of calling it as a pressure equation, the equation of pressure, you can say, by invoking the continuity equation. And we see that this is the idea of a simple method, semi-implicit. You start off with the continuity equation, and by enforcing the guess velocities to satisfy the continuity equation in terms of corrections, we have arrived at the equation of pressure. So the continuity equation is transformed into an equation of pressure correction with the help of momentum equation. All right. Okay. Any doubts? If you observe this. All right. The continuity equation into pressure correction with the help of momentum equation. So here is the second difficulty, that we have a solution of incompressible flow is now addressed using the simple algorithm. Okay. So this right hand side is basically the mass denotes the mass imbalance. This term denotes the mass imbalance, basically your B term. And the moment if your pressure gas were correct, it would yield U star and V star that satisfy both momentum. Because the problem that U star and V star were not satisfied. Initially you guessed a P, based on that you got U star and V star, but they were not satisfying continuity equation. That is why we came with the simple algorithm where from the contribution of the pressure was only taken. Basically we included U star plus some correction. And we put the correction down. We neglect the neighboring coefficient contribution. Only all the burden was over the pressure values. Okay. So from that, we satisfied into the continuity equation. We got the pressure equation. So that means the equation of pressure is basically an equation. If you solve using Gauss-Seidel, you will get P dash equals to constant, right? That will be a solution that satisfies the equation, because AP is equal to summation of A and B. Then P dash everywhere will come out to be constant for the solution. So that means if pressure correction is constant, then what will happen to the velocity correction? Velocity correction would be P prime is constant. Then the velocity correction will go to the zero side. So here, if your pressure correction have computed right, the velocity correction will come out to be right here, in here, because whole of the burden was on pressure values. Okay, on the pressure value. Of course, this constant will make keep on changing, because every time the prime iteration, this might be changing. But P dash equal to constant would tell you that for that particular iteration, you have obtained a velocity field that satisfies the continuity. But we can consider P dash equal to constant everywhere as a converged pressure solution, and that will give you a converged velocity solution. That is UE and Pn. So the velocity corrections are zero. That means we can say that we have obtained a converged UE and Vn. Basically, we want the correction should be zero, and this should come out to be zero, and this should be equal to this. That is the requirement eventually. Okay. Okay. So As I said earlier as well, that it is not the absolute pressure that matters, the pressure gradient that matters. As a result, then incompressible. Okay. We do not have any equation like an ideal gas equation or equation of state where the absolute pressure comes. We have a pressure gradient equations. So as a result, in the incompressible flow equation, only the gradient of pressure that matters. So as a result, your P dash, even if it keeps changing or it is a constant value, it doesn't matter. It does not affect your solution. It should be the pressure gradient that should affect. So now after the velocity correction, essentially your velocities are corrected. Okay. U and V would satisfy the continuity equation and they will not satisfy the momentum equation. Okay. So essentially you have to go back and solve your momentum equation again with the updated pressure because you have got the P dash. No, got the P dash. From P dash, you got the P from here corrected values. You got the U dash and V dash. You got the P dash, then you got the P dash, you got the U dash. Okay. And this U dash you can put in the corrected velocity. Yeah. So you get the U. Okay. So it satisfies both momentum and continuity equation for pressure and velocity. That is the overall algorithm for, for the simple. Okay. Any doubts to anyone? Sandeep, yeah. Any doubts? No doubts? If you have doubts, please ask. So I'll write algorithm in concise way, and then maybe by that we can end the session. Question problems have been discussed by the prof. You can also use the book, solve the equations, solve the questions for this. Okay. Just give me a minute. Okay. So write the complete simple algorithm. Okay. Guess velocity and pressure fields UE star, Pn star, and P star. Solve AE star is equal to summation of A and B U and B star plus del y PP star minus PE star plus PE. Similarly for AN, PN star, you can write this. Okay. Then obtain converged U star and V star and guessed E star. Calculate V terms of pressure correction equation. That is nothing but B is equal to FW star minus FE star plus FS star minus FN star, where you know FE is, where FE star is nothing but rho UE star del Y and Fn star is rho Vn star del X. Then next step is solve this pressure correction equation to converge. To convergence, you can use Gauss-Seidel line by line method, line by line TDA method. Like Gauss-Seidel you can use or line by line TDMA. Then next step, correct U, V, P using UE is equal to UE star plus UE dash, where UE star plus EE into EP dash minus E dash. Similarly, for Vn equal to Vn star plus Vn dash is equal to Vn star plus Dn into Dn Ep minus Pn dash. And P is equal to P star. P. These are the corrected velocity and pressures. Okay. The next step, UV satisfy continuity equation. But not momentum equation. Okay. The continuity is a nonlinear and momentum is linear. Solve for any scalar transport equation. You can solve for transport equation like T, I, and so on to give bounded solution. And you can check for convergence. Go to step 2. by setting. It was an iterative process. You have to go repeatedly. UE star. Next UE star is your UE. Okay. Vn star equal to Vn. P star is equal to. So pressure correction equations drives UV P through your continuity equation del dot U is equal to 0. And momentum equation, you have the corrected fields. That is U is equal to U star plus U dash. And similar for V and V. These continuity equations are used to solve for any TNP. You, when you're calculating the prime velocities from momentum equations, effect of neighboring nodes is neglected. Only the burden is over the prime parts. This is a semi-implicit definition for that. Not fully implicit, semi-implicit. But when you are taking the contribution to be 0, it does not change the convergence of the solution, because at convergence, eventually your U prime and V prime are going to be 0 and P dash is coming to be constant. It is just changing the path to the solution, or you can say your convergence rate, not changing your solution. So for that, you can use under relaxation or over relaxation if it's something speeding up very fast. Under relaxation of some pressure term. Suppose for the pressure term, sometimes pressure fluctuates very fast, so it can be written as P star plus some alpha into P dash. So it's an under relaxation factor. Similarly, for U and U V directly, you cannot write. You have to write it in the form of momentum equations. So like this is for pressure. So for velocity, you will write, you can write with respect to momentum equation as per the algorithm procedure plus your BE plus 1 minus alpha by alpha into AE UE star. Similarly, for north also you can do same thing again. Right. So this is under relaxation kind of. So yeah, so this is up with the simple algorithm. So the questions have been done by the prof in the lecture videos, and they have also done the coding part of that. So maybe we are left with one more week, but an extra session I will be taking up, okay, on 19th of October as well. So the two lectures are still left, one on 15 and then on 19. So you'll get the mail probably, and I'll see you all in the next session. If no doubts, you all can leave. Thank you for joining the session.